Last cool application of L'Hopital's rule, I'm using some of the tricks we learned about last class also when we weren't even talking about L'Hopital's rule. We're going to look at the indeterminate form of 1 to the infinity, which you might be asking, well, why is that indeterminate? Isn't 1 times 1 times 1 times 1 times 1 times 1 times 1, isn't that just 1? Well, the problem is that we're not exactly at 1 to the infinity. We are approaching 1 to the infinity. And if we're approaching 1 to the infinity from a base that's slightly bigger than 1, 1.01, 1.001 to the infinity, well, that is infinitely big. Again, equals infinity isn't really a math statement, but we'll go with it for now. And 0.99 to the infinity is not just, it's not 1 to the infinity, it's a tiny bit less than 1 to the infinite power. But if you keep multiplying a number that's less than 1 by itself, it just keeps getting smaller and smaller and smaller and smaller and smaller, which means it gets infinitely small, or at least it approaches 0. So indeterminate forms means I just don't know what the answer is. And so that's kind of just an explanation of why we need to do more work than just saying like, oh, it's 1 to the infinity. The problem is that L'Hopital's rule doesn't apply to 1 to the infinity. You can't make a fraction out of it. But we do have a cool trick that we can use here. We're going to try and take the limit of x to the 1 over 1 minus x as x approaches 1. And if we want to try direct substitution, that would be equal to 1 to the 1 over 1 minus 1. But as this 1 approaches, as that x approaches 1, you end up with a number approaching 1 raised to a number approaching infinity. Which is indeterminate, we don't know the answer. So here's our really cool trick here. Well, first off, I'm just going to give this a name. I'm just going to call this limit that we're looking for L. The reason I want to do that is because I need to work with it as if it was a y or something like that. So I'm going to give it a name so that way we can use it. Haven't done anything new yet, though. And so we can write that as an equation. L is equal to this limit that we're looking for. And so I'm going to do the same thing I did when we were trying to find derivatives of these weird double exponentials where both the exponential and the base is a variable and we didn't know what to do. We're going to take the log of both sides. And if you remember, the reason why this was useful to us in the last couple of lessons is it allowed us to pull an exponent down. So we're going to do the same thing here. There's one tiny little catch. I do have to first take that ln and put it inside the limit, but you are allowed to do that. The log of a limit is equal to the limit of a log. It's a shortcut way of saying that. And what that allows us to do is pull the 1 over 1 minus x down, still inside the limit, but in front of the log ln of x. So we'll pull 1 over 1 minus x down. I don't really need the 1 because I'm going to fill that numerator with the ln of x. And now I have the limit of a fraction. Now we can say to ourselves, I wonder if L'Hopital's rule will do anything here. So we'll try it. We'll try to establish what we need to. The limit of our numerator as x approaches 1 is definitely 0. And the limit of our denominator as x approaches 1 is also 0. So we can apply L'Hopital's rule. So the ln of, remember, this is still the ln of the limit we're looking for, is equal to the limit as x approaches 1 of, I'm going to take the derivative of ln of x, divide that by the derivative of 1 minus x. And I can do the direct substitution here and say that that is equal to 1 over 1 over negative 1. So the ln of our limit is equal to negative 1. Which looks a little bit like we're done, but we're not, because I didn't ask you to find the log of some limit. I asked you to find the limit itself. We are looking to find out what that L is. Well, all we need to do to find out what that L is solve for it, get it out of that log by exponentiating both sides. So we can say that L, the limit we're looking for, is equal to e to the negative 1, or 1 over e. And it's a little bit crazy that we had a number where we started by saying, I'm not sure, is it 1.01 to the infinity, which would be infinite? Or is it 0.99 to the infinity, which would be 0? No, it's neither of them. It's 1 over e. We want to take a quick look at the graph for that. We can look at the graph of x to the 1 over 1 minus x. And as x approaches 1, well, we know there's going to be a hole there. We knew that we got the indeterminate form. But this number that's getting close to 0.37 something, well, if we compare that to 1 over e, we can see that 0.36787, like that is the number right there.